In our fast-paced, technology-driven world, efficiency is key. Whether you're a seasoned developer or just starting out, optimizing your code for speed can significantly impact the performance of your applications. In this series, we'll explore various strategies and best practices to enhance your coding efficiency. From algorithm optimization and effective use of data structures to leveraging modern tools and profiling techniques, we'll cover a range of methods designed to help you write code that runs faster and performs better. Let's dive in and unlock the secrets to writing blazing fast code. Welcome to Make Your Code Faster. Make your code faster. Data placement for performance. In the ever-expanding realm of big data and resource-hungry applications, optimizing your code for peak performance is no longer just about speed. Efficient code translates to lower power consumption, a critical factor for battery-powered devices, massive server farms, and eco-conscious development practices. While intricate algorithms and ingenious data structures have their place, sometimes the most impactful improvements can come from seemingly simple tweaks. Today's episode dives into a powerful technique, the art of data structure selection, that can significantly enhance the speed and power efficiency of your code, particularly when working with massive data sets. This code explores the critical relationship between data placement and computational performance, particularly within the context of 3D data structures. By generating a large 3D array and performing a simple summation operation using different memory access patterns, we demonstrate the significant impact of cache locality. We compare non-contiguous, partially contiguous, and contiguous access methods, showcasing how optimal memory access can dramatically reduce execution time. This code serves as a practical illustration of how careful data layout and access patterns can lead to substantial performance gains in memory-bound algorithms. The first function, non-contiguous 3D sum, calculates the total sum of elements within a 3D vector, employing nested loops with the order k, j, and I. This specific loop sequence causes non-sequential memory access, as the innermost loop accesses elements that are not contiguously stored due to C++ row major memory layout. Consequently, the processor experiences frequent cache misses, as it must fetch data from slower main memory instead of the faster cache. This disruption of cache locality leads to a significant performance penalty, making the non-contiguous 3D sum function slower compared to algorithms that prioritize contiguous memory access. In summary, the function's loop order dictates a non-optimal memory access pattern, resulting in poor cache utilization and reduced computational efficiency. This highlights the importance of considering memory access patterns when optimizing algorithms, especially for large multi-dimensional datasets. The second function, partially contiguous 3D sum, is the counterpart of the first function. It calculates the sum of all elements in a 3D vector. However, it has a different order in the loops, k, I, and j. This ordering represents a middle ground in terms of memory access patterns. While it doesn't achieve full contiguity, it improves upon the purely non-contiguous approach. By placing the I loop before the j loop, the function ensures that elements along the first dimension are accessed contiguously within each iteration of the k loop. However, the k loop still forces jump across larger memory strides, as the data along the third dimension is not guaranteed to be adjacent. Therefore, while cache utilization is better than the non-contiguous 3D sum, it is not optimal. This partially contiguous approach results in a performance level between the fully non-contiguous and fully contiguous methods. It demonstrates that even partial optimization of memory access, by ensuring contiguity along at least one dimension, can lead to measurable performance improvements. However, it also highlights the continued benefit of achieving complete contiguity for maximum cache efficiency. The third function, contiguous 3D sum, calculates the sum of all elements within a 3D vector, but it does so with a loop order designed to maximize cache locality, I, J, and K. This arrangement is crucial for achieving optimal memory access patterns. By iterating through the first dimension, I, in the outermost loop, followed by the second J, and then the third K, the function ensures that elements are accessed in the same order they are stored in memory. Given C++ row major memory layout, this results in contiguous memory access, meaning that consecutively accessed elements reside in adjacent memory locations. This contiguous access pattern allows the processor to effectively utilize its cache. When the processor fetches a data element, it also loads nearby elements into the cache, anticipating their subsequent use. Because the function contiguous 3D sum accesses elements sequentially, these prefetched elements are highly likely to be used in the following iterations, resulting in high cache hit rates and minimal cache misses. Consequently, this function exhibits the best performance among the three, demonstrating the significant performance gains achievable through cache-friendly memory access. Summary of findings. This empirical analysis compellingly demonstrates the significant impact of data placement on computational performance, particularly within three-dimensional data structures. By contrasting non-contiguous, partially contiguous, and contiguous memory access patterns during array summation, a clear performance hierarchy emerged. Performance comparison and explanation. Contiguous access, leveraging cache locality, yielded the fastest execution, minimizing costly cache misses. Conversely, non-contiguous access, characterized by scattered memory access, exhibited the slowest performance. The partially contiguous method demonstrated an intermediate level, highlighting the benefits of even partial memory access optimization. Importance of data layout and access patterns. These results underscore the critical importance of meticulously considering data layout and memory access patterns when developing memory-bound algorithms, especially for large, multidimensional data sets. Optimal data placement can drastically reduce execution time by minimizing the need for data retrieval from slower main memory. Practical implications and considerations. In practical terms, developers should prioritize data layout and access patterns, especially in performance-critical applications. This includes structuring data to align with cache line sizes, minimizing stride lengths, and utilizing data structures that inherently support contiguous memory access. By consciously addressing these factors, developers can significantly improve the performance of their algorithms, particularly when dealing with large datasets or complex data structures. Thanks for watching this episode about Make Your Code Faster, data placement for performance. Feel free to reach out by email if you have any questions. Next episode is about taming the casting beast. See you in the next video.